All right. Oh, okay. All right. So let's go ahead and get started. Are we good? All right. So, question? I think I am recording now. So I think I just click on the recorder. Yep. All right. So are there any questions about subroutines? How call and how return is done. That's kind of the last thing that we did in class, and also that's what the last lab was about. So are there any questions about the lab, which is due on the same day? Well, let's see, the 11th. So it's due on the same day as our exam too? But are there any questions about that particular lab? No questions? Okay. So what we'll do is we're going to go over the method of calling and returning first, and then we'll continue to talk about how parameters are passed and how we access parameters. Okay? So all of this stuff here depends on a really good understanding of how the stack is organized. Okay, so are we good? Are we good? Are you ready? No? That is correct. There's no actual dedicated area for the stack. So instead of just starting somewhere, I start at the very end of the memory space, and that's why the stack pointer, which is register D, is initialized to 0. Because 0 is also 100 in hexadecimal. So that's why it's initialized that way. All right. So what we'll do today is we'll go through a sample program first, okay, so that we can remind ourselves, how subroutines are done. And then we'll start to parameterize our subroutines. So we'll go back to a subroutine, okay? So we'll do the C version first. This is function f, and this is main. And then we'll call function f twice. Okay, so function f called once, twice, and then main is done. So what we'll do is we'll translate this program into assembly code, just so that we have a quick reminder of how a call is done and also how a return is done. So I'm going to make a new window, and then we can take a look at the assembly code. Okay, so the assembly code, the first thing is there's no such thing as quote-unquote main in assembly code. In other words, your program starts execution at location 0. There's no way you can start execution anywhere else. Can someone explain why that is the case? Why are we always starting execution at location 0 in the toy processor?
Because the stack is 0?
No, it has nothing to do with the stack. No. It has to do with, okay, which register is responsible to tell me where I should go to get the next opcode? The PC, the program counter. Okay. So the program counter is a register, and how is the program counter initialized? It's initialized to 0. That is the reason why we start execution at location 0 in RAM. Okay? So there's a reason why we start execution at that location. So that means if you really want to give main a label, it really should be the first one. Okay, the very first line of your program should be main. Now, if that is not what you like to do, you can always define it somewhere else, but you have to remember to jump to main like this. So your first instruction has to be the main label itself, or a jump unconditional branch to main. Because otherwise, there's no linker to say that, oh, the label main is special, okay, because we have to start execution at main. Your processor doesn't have a linker like that. Is that okay? All right. And then the second thing we do is we initialize the stack pointer. So when we initialize the stack pointer, we load D with a 0, okay? And the reason why we call this a stack pointer is simply because I chose to use register D as a stack pointer. So here comes the questions. Can we use register C or register B or register A as a stack pointer? The answer is absolutely. It's just a convention, okay? The hardware architecture itself does not care. In fact, the architecture itself has no concept of a stack, okay? The whole thing about the stack is only based on how we utilize memory space and how we change the registers and how we utilize the register. There is no such thing as a hardware stack with this toy processor, okay? Whatever operation you can do with register D, you can do with any other registers. Then we go ahead and try to call F, okay? So when you try to call subroutine F, you know that eventually you have to branch to the label F, okay? But the problem is, well, if you branch to label F, and F is a subroutine, okay, I'm going to define F as a subroutine here. It starts with a label definition, so that we know the symbolic name of the entry point of the subroutine. Now, if F is not empty or blank like this and has some kind of code here, okay, then in the assembly version, we'll put those code here, okay? But eventually, that code is going to conclude, okay, it's going to be done. And now the question is, at the end of subroutine F, how do I know where I'm supposed to get back to? What do you think? I mean, you guys did the lab on last Thursday, so what do you think? How can we know where to get back to when we are done with the subroutine? The stack pointer points to what? What is the stack pointer supposed to be pointing at? The stack pointer, at the very end of a subroutine, the stack pointer is supposed to be pointing to the return address on the stack, okay? So that is the assumption, okay? Now, is the return address actually at that location? Well, let's hope it is, because if you make a bug and it is not, then your subroutine will go to some random places, and it will be very hard to explain your program, okay? So we'll just say that, assume the stack pointer, register D, points to the return address on stack. So then, based on this assumption, we can now do LD, and then typically I use register B, not register A for some reason I'll explain later in today's class. So we'll load BD, okay, which means we are loading whatever D is pointing to into register B, and then we say increment D, because that location is now used, and then we do a JMP without the I, very important, without the I, be right there. So these 3 lines of code, lines 6, 7, and 8, is how a subroutine returns, okay? It makes the assumption that a stack pointer is pointing to the return address, back to the caller, in this case, it's supposed to be main. Increment the stack pointer, because that location is now used. I have no further use of that location anymore. So incrementing the stack pointer on line 7 is the same thing as deallocating the stack location that has just been used. It is of no use to me at this point. And then line 8 is the actual branch, to branch back to where the caller is calling from, or the instruction right after the call. Are we doing okay so far with this? Are there any questions regarding lines 6, 7, or 8, seen from the perspective of a called subroutine? Yep? Okay, so a JMP is entirely different from a JMPI. A JMPI instruction will take whatever byte is after the opcode and then use that to tell you where you're supposed to branch to. But that usually is a constant. In other words, you would only be able to continue execution at a particular place, which is not what return is supposed to do. JMP-B, on the other hand, is copying register B to the program counter. So whatever you have in register B is now in the program counter. So this is a far more flexible instruction to use. Okay, so that was a good question, but I'll show you guys how to answer those questions. When you're on your own and you go like, I cannot tell what is the difference between those two instructions. But are there any other any other questions about the sequence of code to perform a return operation in the subroutine? Okay, so in order to make this happen, that means I got something to do before the JMP-IF instruction, because I have to save the return address on the stack first. So that is why we have the LDI. You can use any register in this case. Anything other than D is fine. So you load A with what we call, what I would call main return 1, and I'll put that main return 1 label here. And then the second thing we do is we decrement the stack pointer. So when we decrement the stack pointer, it is the same thing as allocating a byte on stack. Okay? And the stack pointer always points to the last thing that you have allocated and written to. So now we can do an ST instruction like that. So we are now storing store return address on stack. Are we doing okay so far with this code? So if you look at the sequence of code, line 13, 14, 15, 16, and 17, and then you go to label F to continue execution, which is on line 6, 7, and 8, would you be surprised that we end up on line 17 when function F is done? I mean, what is going on with the stack in this case? Well, let's try to figure it out, okay? Line by line, we'll try to figure it out. I'm just trying to think of what is the best way to illustrate this. I think a spreadsheet may be the best. Okay, so we'll use a spreadsheet. Calc, there we go. All right. So I will try to make it match like this. And let's just say that the program has only one function call. So there's a halt instruction here because we are all done at that point. So now we look at all the stuff that is going to happen, all the stuff that's happening. And column A is going to be line number. Column B is going to be register D. Column C is going to be, I don't know, do you want to track all the registers? A, B, C, and D? Yes? Okay. So we'll track all the register then. So we'll track register A, B, C, and also D. But we'll also track what is at location 255. And, well, location 254 is not going to be used, but we'll track it anyway. So now we start execution. We always start on line 1 because that's where the program counter is initialized to when you first start the processor. At that point, registers A is going to be 0. All the locations are zeros at that time. Okay. Is that okay? And then we get on to which line? After line 1, where do you think we continue execution at? Line 10, but line 10 actually doesn't do a single thing, so we'll just say line 11. Is that okay? Because a label doesn't do a single thing. A label has no presence whatsoever when the program is running. It is only there during assembly time so that the assembler can associate a symbolic name with the address of whatever is following. Okay? So technically speaking, we continue execution on line 11. So on line 11, okay, register D gets a 0 again. Okay, it's overwritten with 0 again. Doesn't do a single thing because it was 0 already. On line 13, register A now has the label main return 1. Is that okay? Now, if you guys feel like counting, you can actually figure out what main return 1 is going to be. Line 1 has 2 bytes. Line 6 has 2 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this should be 15. Okay, so I'm just guessing, based on my quick counting, that it's really the same thing as 15. In other words, register A, after executing line 13 or the LDI instruction, register A simply has the value of 15. Okay? Then we move on to line 14. Line 14 says, well, let's decrement the stack pointer. What do you get when you subtract 1 from 0? Not negative 1. We get 255 because it doesn't make sense to treat address as signed. Okay? Is that okay? Okay. All right. Then we get on to line 15. So what happens on line 15? What is changed on line 15? Can someone tell me which column is changed and how we are changing that column? What is line 15 doing? Go ahead. It's storing the content of register A to, sorry? Whatever D is pointing to. So which column should I change? No, which column am I changing? The columns are labeled A, B, C, D, E, F, G. Column F, very good, okay. And how should I change that to? 15, all right, very good. So now we continue execution on line 16, okay. Line 16 actually does execute, even though it doesn't do a single thing. It changes the program counter, that's what it's doing. So we continue execution at label F on line 3, but since we do not execute a label, we do not execute the 2 lines of comments after that, so now we continue execution on line 6, right? So what is line 6 doing? Tell which column should be changed and how that column should be changed. What is the new value of that column? Sorry? Okay, so which column is getting changed? Column C is getting changed, and what is the new value of column C? There's a reason why there's a pair of parentheses. What do you think the pair of parentheses are indicating? D reference. Okay, so we are not copying register D, we're copying what register D is pointing to. So what is register D pointing to? What is the value that it's pointing to? 15, all right, so register B is now updated to 15. Then we go to line 7, which is increment D. So we are incrementing 255 by 1, so it becomes what? 0, very good. And then on line 8, we do a JMPB. A JMPB is really the same thing as the program counter getting register B. So it means it doesn't really do anything. There's no column here that is changed because I'm not tracking the program counter. But as a result, where do I continue execution after line 8? I will continue execution at location 15, right? Location 15 also has a symbolic name of main underscore return 1. So where is that in the source code? Which line am I continuing? Line 18. But once I get to line 18, I cannot get out because it's a halt instruction. So that is the path of execution. And you can basically see how we are utilizing the stack, which is location 255 only in this particular program. It only uses up 1 location. But that is how we keep track of the return address. Is that okay? The caller sets it up. The subroutine consumes it. Are we good so far? Yes? Okay. Yep.
We did not reference D on line 6. What
On line 6?
Yeah.
So, sorry? On line 6, we did dereference D because that's how we got the 15.
I mean, if we didn't dereference.
If we did not? Okay, so now you have to clarify what you're saying. Are you saying that you do not put in the parentheses?
Yeah.
Or are you saying that you use a different instruction?
You do not use the parentheses.
Then it will say it's a syntax error. Okay. The assembler makes sure that you use parentheses as a visual indicator that it is dereferencing that component.
All right.
If you want to copy a register to another register, it's CPR, which is copy register. Okay? All right. But this is just what I'm claiming, right? So, given that this is the code that we are talking about, and I'm saying that this is all going to happen, and it's basically modeling this particular C program, what are you going to do? I mean, I introduce some material. I introduce the concept of a stack, the concept of how a call is done, how a return is done. What are you going to do after class when you're studying? How do you study for this kind of material? Okay, you can assemble, run it, right? But when you run it, there's no visual cue whatsoever, right? Because when you run it in the simulator, it doesn't give you a trace like this, okay? There's no visual indicator except, it ends up at the halt instruction. And the halt pin, is a 1. So how do you look at all this stuff and be able to understand it the way it is presented here? Yep. Log it, and then use the trace analyzer spreadsheet to help you reconstruct the sequence of what location, what register got changed, when, and how. Are we doing okay so far with that? What if you have another question? What if your question is, I don't really understand how store is different from load, the LD instruction versus the ST instruction? How would a person answer that question? You hand trace it. Well, the best way to do it is to hand assemble the LD instruction or ST instruction. Pick 2 registers. Okay, it doesn't matter. You can pick the same registers that I have used here on line 15. Okay, so you look at the opcode table. You hand assemble that opcode. Okay, and then you use that opcode to look up the ROM location in the processor. That's going to give you a 7-digit hexadecimal number. And then what do you do with that 7-digit hexadecimal number? You hand decode it, okay? You can use a spreadsheet, okay? And one of your fellow classmates has made a spreadsheet to decode, a 7-digit hexadecimal number, and I think it's also commented too, so you know which signal is going where. So I can share that with the class, and in fact, he insisted that I share it with the class. So you guys can use that, okay? Then what do? Now you know what value is going to which tunnel. Then what do? You look up, you get a printout of the processor, and then you track down, okay? Which multiplexer is what value, which register is enabled, which register is ready to be updated, how the paths are connected, is RAM being selected? If so, are we reading it or are we writing to it, and so on. That is how you study when you look at instructions like, I have never seen the ST instruction. I'm not really quite sure what it does. That is how you answer the question yourself. Do we have any questions about that process? That process is not going to be easy, but that's how you learn how the processor works. Are we good so far? Does anyone want me to do it? Here? Now? No? Okay. Yep.
Could you maybe demonstrate the tracer that you built one more time? Because if I recall correctly, last class when you tried to use it, something wasn't working properly.
You are correct. I do remember that something was not working. So let's go ahead and do this. Okay, so I'm going to assemble the code and then go to one of the... Oh, by the way, this is the opcode table. This is how you hand assemble a single opcode. So if you're interested in the ST instruction, you go to the ST instruction, which is this row here, and then you just say, oh, we want to store register A to where D is pointing to. So Y is D, which is a 0, which is 1, 1, okay? And then X is register A, which is 0, 0. So the entire opcode is going to be F3. Then you go to F30 in the ROM, get that slice of microcode, decode that microcode, and then figure out the pathway within the processor. Okay? All right. So I kind of forgot what I was about to do. I think I was about to assemble the program. And it says I have been signed out. Okay. That's okay. I can sign back in. Now, if anyone is thinking that I'm assuming too much, that you can track down, how the processor works, just like what I said, you have to come to me and explain to me which part you're not understanding, that you cannot follow. Then I will try to help you understand that process, or whatever step you're missing. Okay, but without people actually telling me that, I'm going to make that assumption. All right, what is that? It's a capybara. Capybara. All right, so we have the output over here. Download as CSV. So this one is just call return, like so. And then we have to start the assembler. So I have to go pick one that is around here. Oh, one is here. It's just really hard to get to. There we go. Oops. Okay, I think I'll start a new one. Because you guys probably don't want to read that small of a font. Okay, there we go. There we go. Okay. So to do what we talked about last time, you have to oops, that's not what I want. I want to find from my history how I ran Java, and the last one was here. So this is how you run, Java in order to use the automatic way of tracing. So I'll just kind of briefly go over this again, because I talked about this already. We have Java, which is the name of the virtual machine, -jar to specify logisim as a jar file. Processor 003.circ, that's the name of the processor. -load, this is what you want to load into the RAM component of your processor. -tty table, that is something that you do not want to change. What that says is it tells Logisim to not start up in GUI mode and instead start up in console mode so that the output is generated onto the console. This is the redirect symbol. So whatever output is coming out of Logisim is now captured in this file. The file has an intentional extension of TSV because it is a tab-separated file. Okay. So that's kind of the command that we want to run. And in order to run this command, I'm making the assumption that I am where the processor is located. So that's my folder here. All right, so cool. So I can now copy and paste, except the file that's containing the program is not test anymore. It is call return, like that. So you run the code, and then the log.tsv file is going to be a trace. Okay? This is really difficult to understand because it has no column heading whatsoever. So what you do is you go back to my shared folder, and I cannot remember where I put the trace. Oh, okay. This is where I put the trace analyzer. Go to sheet 1 of the trace analyzer, and then you go to File, and then we do an import, upload, and then we pick out that file, which is call return. Nope, that's it. That's not it. It's log.tsv. Okay, let's do it one more time. So we go to import, upload. It's log.tsv. There we go. And then you have to pick the right options. Replace current sheet. Use tab as the separator, and say no to convert text to numbers, dates, and formula. Click OK, or import data. Now we have all this in sheet 1, and then sheet 2 has a very clean representation, all in hexadecimal. All right. So not all the columns that we traced earlier are here. We do have registers A, B, C, and D. And you can see that this trace is a little bit longer because it traces every single transition. So you have to kind of understand what is being changed between the lines or between the rows, and whether it has significance to you or not. Is that okay? But we do see how register D got changed to FF, and how it got changed back from FF to 00. We also see how locations are overwritten. So if you want to see how locations are overwritten, you want to look at RAM cell, okay? And you also want to look at data, which is the data port of RAM. And you also want to look at address, which is the A port of RAM. So we can actually see how location FF was overwritten right here. And according to this, it's overwritten to 0D. So I miscounted. I miscounted because I thought it was 15, but 0D is only 13. So my counting was off by 2 bytes. But you can basically identify, which row is overwriting RAM and what is going into that RAM location. So are we doing okay so far with this trace or not? We good? All right. So this trace table is optional. It is just a tool that I'm providing so that if you guys want to find out what's happening when you run your program, this is one way to help you visualize that process. Because otherwise, it can get kind of difficult to figure out what is going on when your program runs. Yep?
Why is the RAM clock column mostly 0?
RAM clock. Let's see. RAM clock column K. They're all zeros except for this one. So this one is when we have a transition of the RAM clock going from 0 to 1, and then it tracked it. So the question is, how come it did not track it otherwise?
Yeah.
That is a good question. Because the simulator is supposed to log an entry whenever. Oh, I know why. Because RAM clock is not the actual clock. It is gated. So RAM clock does not change unless RAM is selected and RAM load is a 0. So if you look up this row here, when RAM clock is a 1, I think you should find that RAM select is a 1, RAM cell is a 1, RAM load is a 0. So the intention of RAM clock is so that we know what is written to RAM. So the idea is if you see RAM clock being a 1, you want to track 2 rows. And these 2 rows together indicates a rising edge. And the rising edge is presented to RAM when RAM load is a 0, meaning that we are writing to RAM, and RAM cell is a 1, which means we are addressing RAM. So when you look at these 2 rows, the address will tell you which location we are addressing, and then the data will tell you how we are changing that location. So is that okay? Yep, go ahead.
This is when the ST opcode.
Yep, this is because of the ST instruction. Of the entire program, the ST instruction is the only one that can change a memory location. And I should make it more general. Of all the opcodes, okay, the ST instruction is the only one that can overwrite the content of a location in RAM. Every other instruction can only read. ST is the only one that can write. Is that okay? Any other questions about the trace table? No questions? Well, if there are no questions, we're going to talk about other stuff. Are we ready for the other stuff? Okay. All right, so getting back to the notes here, okay, getting back to the module, we are pretty much done with stack operation, but in terms of the modules, we are now getting to parameters and local variables. Okay, so this is where we are located here in terms of the nodes. So we'll take a look at this module. And parameters are stored on the stack. Are you surprised that the parameters are stored on the stack? Oh, are there any questions about the program that you ran on last Thursday, which is recursive? No questions? Okay, how about this? I'm going to change the program a little bit in C, and then I'll see if you guys know how to translate that back into assembly. Let me get rid of this. This is from my 440 class. Okay, so here's another program. It's still pretty useless because G calls F. And in main, we're just calling G like that. So now the question is, can you rewrite this program in assembly code based on what we have talked about earlier? I mean, conceptually, I know there's a lot of detail to take care of, but conceptually, do you know enough to write this code? Okay? So let's go ahead and do it, right? There's a whole lot of copying and pasting because subroutine G, for the most part, is just like subroutine F. It doesn't do anything. Okay? But it has one thing to do. It has to call F, right? So now the question is, how do we call F? Well, we got this bunch of code here to deal with calling. So we copy and paste this into here. But we have to remember to change a few things, okay? So this is a prefix of which subroutine the return label belongs to. So it's G underscore return 1. So we'll change this one to G as well. And it's calling F, so we're good there. And then when we get down here, main is not calling F anymore. Main is just calling G. And that's it. That's all the changes I have to make to the program so that now main is calling G, G calls F, and F doesn't do a single thing and just returns. So are we good so far with this code? But what do you think the stack is going to look like? Or what kind of memory operation we're going to perform to the stack? Main is starting first, okay? So we are starting execution basically practically on line 23. Initialize the stack pointer. We push this return address on the stack. So the return address that we know as a label, which is main underscore return 1, is going to use location 255 in RAM, which is the highest location in RAM. Is that okay? Then we go to G. Okay, so what is G going to do? G is going to call F. So in order for subroutine G to call F, it has to set up its own return address on the stack before we continue execution in F. So that means we are going to push another return address on the stack. This time the return address is the label G underscore RET1. Which location is that going to take up? Location 254. Okay, very good. So once that return address is pushed, we go into F. So now we continue execution in F, which is not doing anything too exciting. It is going to get the location 254 back, or the content of location 254 back into register B, increment register D. So can someone tell me before the increment, what is the value of the stack pointer at this point? 254, that's right. So we increment it back into 255, and then we do a JMPB. Where is this JMPB instruction going to lead us? To which label? G underscore return 1. Okay, so we continue execution here. So guess what? We are going to use the stack pointer to retrieve a byte on the stack and then put it into register B again. But this time, what is the value of D itself? 255. What is at location 255? Main return 1. So now we are copying main return 1 into register B. We increment the stack pointer again. It goes from 255 back to 0. And then we branch based on the value of register B. Register B is now main return 1. So that means this branch instruction will land us here in the halt instruction of main. So that is how call and return works. Okay? Calling is always going to look like this. Okay? This is how we call. Returning is always going to look like this. Do we have any questions about how we call and return? No questions? All right. So I will leave it up to you guys to kind of copy and paste this program and run it and understand how the stack locations are being used. So I can save it and post it to Canvas so that you guys can have a chance to play with this without having to retype everything. So I'm going to save it to FG main. Okay. So the source code, I'm going to use TTP-ASM as the extension. And then we'll go to Canvas. And I'll just do it in an announcement so you can check your email if you want to play with this program. So FG main. And okay. And then we go to here. There we go. All right. So as soon as this one is posted, now you have a choice. You can choose to download this program, look at it, trace it, track down what it's doing, or you can ignore it. It's definitely your choice. But guess what? At the end of the semester, it's your grade too. All right. So now we're moving on to parameters and local variables. In other words, let me switch back to C mode first. Okay, so I'm going to go back to C over here. And let's go ahead and combine a few things. Okay, I'll just get rid of this. And we'll have F to return a value. So I would say this is returning an int8 underscore t. And it returns 5. Okay. And in main, I'm going to allocate a local variable. We call it x. X gets the return value of f. Okay. So now we have a C program that is slightly more complex than before. Still pretty useless, but it has a few more features now. We have to know how to return a value. Like on line 4 of the C code, it returns a value of 5. How do we do that in assembly code? I'll tell you the answer is so simple, you guys will go like, okay. Then we have to worry about line 9 and line 10. How do we allocate space for local variables? So are there any questions about what local variables mean in C and C++ programming? Are there any questions regarding, okay, do you guys need any clarifications of what a local variable is and how it is different from a global variable? Any questions like that? Nope. Okay. How many people have the question of what is a static local variable and how is that different from an auto local variable? I mean, were those concepts even introduced, the concept of a static local variable? I see some people shaking and some people nodding. Okay, so So I guess we don't have to go over that because unless somebody introduce both concepts, there's no need to differentiate. Yep. Yeah, go ahead. Yeah, you. No, static means it is kind of like a global. So the difference is static, there's only one static local variable for all invocations of the same subroutine. If it's not static, it is automatically auto, and that means for every invocation, there is a copy of that local variable. Okay? All right. So we'll look at this program and see what we're going to do to code this. Okay? And we'll do it the same way as before. Okay? So I don't like to modify the program too much, so I'm going to start from scratch here. We'll do a JMPI to main and worry about main later. Okay? So now we want to deal with F. Well, the funny thing about F is it's not really that much different from before. So can someone remind me again, what are those three instructions to do the return? LD, BD, right? Because the stack pointer is assumed to be pointing to the return address. Increment D in order to deallocate that location on the stack because we are using it right now, and then JMPB. Okay, but Tech, how do we do the return statement? This is how we do it. LDI A5, okay? What does that mean? It means exactly that. It means exactly that we are putting a value of 5 into register A. Then you ask, but what does register A have anything to do with the return value of a subroutine? It is just a convention. It is just a convention that any scalar value, like integers, floats, pointers, and stuff like that, is returned by register A. It is just an agreement between the caller and the subroutine. The caller says, hey, subroutine, do stuff. Okay? When you're done, I'm expecting the result to be in register A. That's what the caller is saying. The callee, on the other hand, is saying, okay, I'm going to do some calculation, blah, 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 blah. Okay? I'm all done. Where am I supposed to put the result of the calculation so that the caller knows that this is the result? Right. There's the agreement, register A. And that's it. This is all there is to it when we say, how do we return the value? There's a question back there.
Yes, then it overrides whatever A was in the main.
Yes, every time you do a LD or LDI, the first operand is always overwritten. Yep. But is this special? Is register A special to the processor? Nope. It is just how we use it that is special. Okay? It's just like register D. This is all about convention. Okay? There's nothing in the architecture itself that says return values must be in register A. There's nothing like that at all. It is really just a convention that we use register A to specify the return value. Yep.
So we could use any other register.
Not in this class. When you write your own compiler, yes. But in this class, because we are using my convention so that my code can interact with yours, so we have to use a single convention in this class. So are we good so far with how to return a value from a subroutine? Whatever value you want to specify to return, put it in register A. It's really that simple. Okay, follow-up question. Is this really the same thing, when we are talking about commercial compilers like GCC or Visual Studio and stuff like that? And the answer is, surprisingly, yes. Okay? Except in the case of the Intel processor, we are not using register A. We're using register EAX in 32-bit mode, and we're using register, I cannot remember the 64-bit mode register. Does anyone know, remember? It's something AX, okay? So it's the same convention. It's just that the register that we choose to use in a real architecture is a lot bigger. It's not 8-bit wide, it is 32-bit wide or 64-bit wide. But the convention of using a single register to return a value from a subroutine, that's an industry standard. Yep.
In our C code, return statement is like at the end of the subroutine.
Yes.
In our assembly code, our return statement is in the right after the label.
Yes. So the label is only here to indicate the entry point of the subroutine. Where does it start? That's what the label is here to do, is so that we know where the subroutine is starting. Okay. All right. What about main then? Okay. So main, we got a few things to do. We have to initialize the stack pointer. Okay. D has to be initialized to 0. Now where am I going to put the local variable x? We're going to put it on the stack. In other words, this is what we do. Decrement D, reserve a spot for local variable x. That's how we do it. We just say, hey, we want location 255 for our local variable x. Are we doing okay so far with this? That's it. This is how we reserve the spot, okay? And then what do we do? What is the rest of the program going to do? Kind of the same stuff that we have done already, right? Remember the return label. And we decrement D again, because this time we have to remember the return address, which is also on the stack. So we do a stda. So at this point, 2 locations on the stack are now in use. Location 255, which was reserved first, was our local variable x. Then you might ask, but what is the initial value of local variable x? Do we know? Do we care? No, we do not care, because this is only a declaration. All it says is, I want to have available to me a local variable. It doesn't do any type of initialization, so neither am I doing any initialization on line 12. Is that okay? The second byte on the stack that is now in use is location 254. Location 254 is now used to remember the return address back to main. Okay. So at this point, now that I have remembered where the subroutine should go back to in main, I can now transfer control to the subroutine, which is in F. Then we have the return label specified here, which means when the subroutine is done, it will do 2 things now. It will first put a value of 5 into register A, because register A is, by convention, what we use to return a value. Then it will do a branch. Okay? It will go to the stack, retrieve the return address, put it into register B, and then do a JMPB, so that now we continue execution here. I don't want to put a halt instruction here because I'm not done yet. What else do I need to do in main? Where am I here? Where am I in main at this point? I'm still on line 10, am I not? Because I'm just done with calling F. I'm not done with the assignment yet. So now the question is, how do we put that return value into local variable x? It's a 1 instruction thing. Okay? So what you need to do now is to think about what is register D at this point on line 19. 255. And what did I reserve location 255 for? Local variable x. Oh, wait. So you're telling me that the stack pointer is pointing to the local variable that I need to overwrite? And what about the return value? Which register is containing the return value right now? Register A. So I need to copy register A to where register D is pointing to. Can I do that with 1 opcode? That's what we do. Because at this point, we know that register A has the return value. We know register D is pointing to the local variable x. So a single store instruction is all we need to do. And then at this point, now if I really want to end the program correctly, this is what I need to do. This is for D allocating local variable x. Then I can halt. Even though, if I don't do, line 21, it doesn't make too much of a difference. But in terms of having the stack to remain balanced, this is actually important. So at the end of every subroutine, you need to deallocate the storage used by all the local variables. Yep. Yep, this is how C and C++ code does it too. Yep.
So,
Yep.
so return 0, you say it's the same as home?
Say that one more time.
Return 0 on the C code is basically home, is that what you're saying?
Yeah, because this main has nowhere to return to, so all we can do is just to say halt.
So you wouldn't do LDI?
No, nope. Because the stack is empty at this point. There are no return addresses stored on the stack anymore. So our main is very different from the traditional C main, because this so-called main really is not a function. We did not get here because of a call, so we don't have a place to return to. So that's a good question, but I'm glad that we can clarify that point. So are we good so far with this code? Yes? Yep.
How many local variables can we assign with 4 registers?
Say that one more time.
How many local variables can we assign with the 4 registers that we have here?
Well, okay, so the question is, your question is how many local variables can we allocate since we only have 4 registers? So now the question is, where is the local variable? Is the local variable in a register or is it somewhere else? So if I want, if you remember, during the execution of the program, do you guys remember that line 19 is what is going to store a value into the local variable x? Do you guys vaguely remember that? Okay. So what is changed? Is register D changed, or is where it points to changed? Where it points to, right? So the local variables are not in registers. Where are they? They're on the stack in RAM. So there's no limitation. As long as you do not run out of RAM, you can have as many variables as you want. Any other questions? Yep.
How would you keep track of multiple local variables if they were not, say, in the same order?
That's a very good question. Okay, so to answer that particular question, so let me just repeat the question first, because the mic doesn't pick you up. So the question was, if you have multiple local variables, first, what is the ordering of allocating those local variables? And number 2 is how do we keep track of those locations so that we can actually get to the right spot for the right thing? Okay, so there are at least 2 questions involved. We got about 20 minutes. So in order to answer your question, let me introduce yet another concept, but through that concept, we'll be able to answer this question of yours. Okay? So now we make the program slightly more complex. We say it has a parameter now. So we have a parameter x, and we want to return x plus 5. Okay? So when you look at the C code, it's not complex at all. But if you look at the assembly code, then it's like, oh no, we are throwing another concept into this whole thing. So now the question is, what do we do about parameters? Okay, you got a few choices. You got 2 choices basically. Okay, where do you store the parameters? You can store the parameters into registers. But wait, we already use register D as a stack pointer, so we cannot touch that one. And then we only have 3 other registers left, right? I think that's a limitation. If you say that you can only have up to 3 parameters, I'm going to cry. Okay, so that option doesn't work out, okay? Putting parameters into registers is not a good idea. So we have to put it into where? RAM, but to be more specific, the stack, okay? So we push parameters on the stack before we call a subroutine. Then the subroutine has to retrieve that parameter from the stack. Okay? So now we go change this program and say, okay, we'll put a 7 here. Okay? So we are calling f now with a parameter of 7. So what do we need to change? Well, let's change the caller first. So we are now changing the caller so that we are pushing the value of 7 as an argument first. So we say load A with 7, decrement D, allocate a spot on the stack, store 7 onto the stack. Okay? So these 3 instructions together is pushing the value of 7 on the stack. Do we know what the word push means in the context of a stack? Okay, very good. Okay, because I think that's part of the exercise last Thursday. Okay, so we're pushing 7 on the stack, and then this one is really just pushing the return address on the stack. Can somebody tell me where in memory is this 7 stored? Location 254, very good. So 253 is now the return address because we keep putting more stuff on the stack, right? Okay? All right. So the next thing we want to do is now we go into the subroutine and go like, okay, tech throws another wrench into this whole thing. We now have to go retrieve x from the stack, okay? Because we have to say x plus 5. So what I'll do is I'm going to show you the code first, and then we'll talk about it. We do a CPR first. Now CPR, just like any instruction that can modify a particular operand, the first operand is the one that is being changed. So if you want to copy register D to register C, this is how you do it. Okay? So the command is, okay, C is now D. They are the same. Okay? Tell me again, what is register D pointing to at this point, right here at the entry point of a subroutine? What was the last thing that I pushed on the stack before I get into the subroutine? The return address. Very good. Okay. But it's not the return address that I need to access. What do I need to access again? In order to implement line 4 of the C code, what do I need? I need the parameter, right? Where's the parameter relative to the return address? +1. Oh, okay. So that means if I increment C, then C becomes the address of parameter X. Is that making any sense? No, I'm confirming that it is. Okay, maybe that works better. Okay, so what you need to do, okay, I'll finish this code first, and then we'll kind of track down what is in memory, at each point. Okay, so we load I with A5. Okay, so we do add. Wait, C is the address of X. How do I get to X itself? In other words, C right now is 254. That's not 7. Indirect. And which opcode should I use to indirect? Load. That's right. Okay, so we can load C like that. So now C is actually X. Is that okay? Because we just dereferenced the address of X. And then we can do an add AC so that X is added to the 5 that I have already put into register A. We're done. Then we go back into the main subroutine, and we got one more thing to do. Because right now at this point, what is on the stack when I get back to this point? I have the parameter on the stack. Do I still need the parameter? Nope, the call is over. Why do I need the parameter on the stack? Increment D, get rid of the parameter. So the program is done. So now we need to kind of comment everything and so that we know what is where at this point, okay? All right, so what we'll do, let me see. I'll do a trace just like last time. So we'll put this code kind of on one side, get my spreadsheet back here, and we'll add a new sheet here. Same as last time, we got register A, B, C, D, and then we got RAM location 255, which is my local variable x in main, 254, which is my argument being pushed to function f, 253, which is my return address. So up to 3 bytes are used on the stack with this particular program. Oh, I forgot about the line number. So insert column, line number. There we go. Okay, we're good. Line 1 doesn't do much. Okay, all we do is get to line 15, right? Are we good so far? Because line 1 just do an unconditional branch to main, and that's all it does. And then on line 15, register D is initialized to 0. Okay, doesn't need that much space. On line 16, we decrement D so that register D is now 255. On line 18, register A gets a value of 7. Is everybody still following me? Okay. Line 19, we decrement D again. So it now becomes 254. On line 20, we store to register where register D is pointing to. So which column should I change? Column G, it should be changed to 7. Very good. All right, so continuing to line 22. Line 22 will store the return label. I'm going to abbreviate here because otherwise it takes up too much space on the cell, in the cell. So we store return 1 as a label to register A. On line 23, we decrement D again, so it is now 253. On line 24, we do another store. Tell me which column should be changed and how I should change it. Column H should be changed, and what is the value I should be storing there? RET1, okay? It's supposed to be main return 1, but I'm not using the entire name because it's too long. So return 1 is being stored here. But do you see how the stack is being used? This is local variable x of main. This is the argument that we are passing to function f. This is the return address, so the function f knows where to get back to when it's done. So are we good so far? Okay. After line 24, we execute line 25. Line 25 doesn't really do anything particularly useful other than let's go ahead and continue at label f. So now we continue execution at label f. So now we get to line 4. Line 4 says just copy, okay? It's just copying whatever D has, so that C has the same thing. Register D has 253, so now C also has 253. Line 5 says add 1 to it, 254. Line 6 says register A now has a value of 5. Line 7 is loading C with C. Okay, what are we doing here? We're loading indirect C into register C. In other words, we first follow register C to where it points to in RAM. Register C is pointing to location 254. We go to location 254 to retrieve the value of 7. What do we do with that 7? We overwrite register C with that 7. Okay? So register C is now 7. We then move on to line 8. We add register A and register C, but we store the sum to the first operand, which means register A is the one that is getting overwritten to a value of 12. Very good, which is the return value. On line 10, what do? We load BD, okay, which means we go to where register D is pointing to. Register D is still pointing to location 253. We go to that location. It has the return label of return 1, and we put it into register B. Okay. Oops, I said register B. There we go. On line 11, what do? We add one to register D. So register D is now pointing to 254. We go to line 12. We continue execution where register B is pointing to. Register B is saying, oh, let's go to the label main underscore return 1. Okay, so we scroll down here. We go to main return 1. So we continue execution at this point at line 27. Line 27 says increment D. So register D is now at location pointing to location 255. And then we on location on line 28, we do a store. Register A, which is 12, is now stored to location 255. So location 255 is now changed to a value of 12. And then on line 30, we increment D one more time. So it is now 0. And then on line 31, we're done. So this is, yep.
If we put the program into the OnSim and then we single clock that all the way to the end,
Yeah.
at location 255 around we find 12, right?
Yes.
But register D would be 0.
Yes. At the halt instruction, yes. So any questions about this one? No? No question or not understanding? No question, okay.
So value 12 now in register A and
So register
in register 12, right? Register A.
Register A is only special when you're dealing with the last instruction of a function. During the execution of a function, register A is like, you can use it just like any other register.
So my point is tracing the code from line 16 in spreadsheet. So register
Row
A,
6, you mean here?
yeah.
Okay,
So register A has value 12 stored in it.
right.
And then if you keep going, line 21 didn't change register A. It's still 12 there.
Yes. Because the main program has not done anything with it. Because when you're done with the subroutine, we continue execution here in the main program, and it doesn't do a single thing with A, and it only makes use of A, it's only reading the value of A on line 28.
So my question now is, what's the point to copy value 12 from register A to the stack?
It is because we want to implement the C code to store the return value into local variable X. So remember, we are trying to implement the C code here. So the storing, the ST instruction in main has to do with this assignment operation. Is that okay? Kind of okay? All right. So you can see that a lot of stuff is on the stack. So now the question is, I have about 5 minutes left, because I was about to show you a program that I can write in C that can give you a symptom that you cannot debug without knowing the stuff that you now know in this class. You can mess up the stack by accessing an array out of bound. That's not difficult to do, right? So tell me what you learned in your cisp310 class. Did your professor say anything about what happens when you access an array out of bound, especially a write access out of bound in a subroutine? They never talked about it? Say that. It will be overwriting something, right, on the stack that is not what you intend. Right. So from our discussion today, do we know what else is on the stack? We know the return address is on the stack. We also know the local variables of your caller is also on the stack, right? So when you access an array out of bound and you're overwriting some location on the stack, you could be overwriting, let's check what you could be overwriting. You could be overwriting other local variables of the same subroutine, okay? So things will be garbled, okay? You could be overwriting the return address on the stack. Now, if you overwrite the return address on the stack, what do you think is going to happen?
Even if
Nothing is going to happen until you attempt to return, right? Because when you attempt to return, you'll be using a garbled or overwritten return address. If you're lucky, that return address is totally invalid. Your program just bombs out, it crashes, and that's the end of it. If you're unlucky and you incremented that location or decremented that location, then the address is still quote-unquote valid. It will bring your program to somewhere, except it's not where it is supposed to be. So your program won't crash, but it will do something that's totally wonky that you cannot explain at all. But there are even other things on the stack too. There's also the frame pointer, which we won't talk about in this class. If you override the frame pointer, the symptom is going to be even more fun because the subroutine itself is going to be fine. It will return to the caller just fine. But the caller itself will now access all of its local variables shifted. So, what used to be variable X is now variable Y. What used to be variable Y is now variable Z, and so on. And without understanding, what the stack is, what the stack pointer is, and what is stored on the stack, you would not be able to debug those programs. You'll be looking at that program and just be scratching your head and go like, what happens here? Yes? I will show you all of those cool stuff next class, next Tuesday, sorry, because Thursday is our exam. So next Tuesday, I will show you all kinds of cool stuff. Like you can call a subroutine and it returns to another subroutine that is called from nowhere in your program. So I'm not going to give you guys any new lab today because you guys kind of have to study for the test. I will be at the lab, okay, to help you finish the lab that we started on last Thursday, and to answer any questions related to the exam. Yeah.